Hi, my name is Adnan Munir, and today I will try to explain the selected paper from the list. And the title is Exploring Depth Information for Detecting Manipulated Face Videos. And here are the list of the authors. So first of all, we will try to see the introduction. What exactly the face manipulation we know today's in the AI era. So most of the people use the deepfake technique, especially the GAN or the diffusion model, to just falsify the videos or maybe the post significant security and reliability changes. So that's why they require advanced detection method. So nowadays existing method struggled with on generalization between different data sets. So for that purpose, and also the available methods was not considering some auxiliary feature information techniques by adding in convolution networks for the face manipulation techniques. So the main motivation for their paper was came from this figure. We can see from this figure, these are two different data sets, like the FF plus plus face forensic plus plus and the Calib DF. If we see if the images are clear and the original, the depth map of the face is very regular and the clear. Even for the residual the features, the map depth map is a very regular, uniform. But if we see the fake, if there is AI generated image or the deep fake image or the manipulated image, we can see the depth map of these type of images are irregular, and most of the information spread out throughout the corners. So that's why the author consider the this auxiliary information, the depth map, uh, for the sake of finding the face manipulation or the deep fakes. The key contribution in the paper, they have introduced these three main modules: the face depth map transformers, the multi-head depth attention, and the RGB depth inconsistency attention. What are these modules and what they are doing with them, we will see from the next slides. So here in this slide, we will try to see the full overview of the paper, like the overview of the proposed model, like how they propose the model and how their model works. The first step is like the input, there, because it's on the video, so they're providing input, the sequential phase frames from the videos they're extracting. And after extracting, they're passing the phase frames to the backbone, and similarly they're passing these phase in non-overlapping, they're dividing in patch embeddings and the sequence embedding. And because they're using the transformer, the vision transformers technique in the backbone, because they have to extract the feature from the RGB images and from the different channels. So they are using the backbone as an exception. Because they are in ablation study, they have used different, but mostly in their model they are using the exception. And after that, we are using the MDA, their proposed multi-head depth attention. What exactly multi-depth head depth attention is doing? It's actually the merging the face depth, the face depth maps and the RGB feature maps. And after fusing these maps, they are passing the enhanced map to the the RGB depth inconsistency attention. And again, here they're enhancing the feature and the temporal relation of the frames, and then they're passing to the 3D CNN to just check either is the real image or the deep fake image. So this is the main overall overviews, but we will see from the next slide one by one about the. So first, let's see about the phase depth map transformer, how it works. Here we can see the phase depth like transformer, what they are doing. The frame from the previous, we can see the RGB channel are coming, and it is dividing into the patch embeddings, and then the sequence embedding, and then they move forward toward the transformer, and in that they are using normalization, the multi-head attention, again normalization, and multi-layer perceptron, because same like the vision transformer does. And after the fully connected layer, and after this, they are getting the depth map of the RGB images. And but in the phase depth map transformer, they also using the supervised technique. What supervised technique? They are using the ground truths, the real face images, face depth map as a ground truth. And for the real, for the ground truth, they are using already the state of the art model for getting the original face depth maps. So so with this transformer, they are getting the face depth map, uh, which is actually exactly same like the vision transformers. But the depth value, how they are like in the ground truth, if the face is fake, and or maybe if it's not face, like the background area, then the depth value will be 0. And if there is a real image, so the depth value would be between some lambda and 255. So lambda is any number real, any integer, real number, integer. So after getting these phase depth maps, if we go back, so after getting this phase depth map, and from the backbone they're getting the feature maps. No, the MDA multi head depth attention will be used to fuse or to merge these two features. So here they introduce the MDA multi head depth attention. Again, the objective is to effectively integrate the face depth map with RGB feature coming from the backbone, and the depth map coming from the FMDT. And then what exactly, because how we have to see like the FM, like especially the phase transformers. We are getting the depth map, and in the backbone we are getting the RGB feature. So what they are doing here, they are doing the dot product, because dot product give us the correlation between this RGB feature and the face depth map features. So and here WR is the RGB weights and WD is the face depth, and they both are the trainable weights. And they are doing the simple dot product by get and why dot product? Because they're getting the correlated feature, like those features from the face depth map which are correlated to the RGB features, and they applied the softmax to just nullify the negative values and getting the positive values. And here these weights or these features are called as the depth attention, because these features are those from the depth maps, those have some correlation with the RGB features. And again after that, here they are mixing or the fusing with the original RGB with these weights. These are also the trainable weights, and here they are mixing. And here the enhanced F dash RGB feature map scheme. After that, they are applying the here, because again they are adding the original RGB and the enhanced RGB feature maps, and they are passed to the MLP multi-layer perceptron just to add the non-linearity, or to just learn more non-linear attributes from the RGB data. And after that, they are getting the enhanced features from the multi-head. So when they will get here the enhanced feature, we will see from here they are getting the enhanced feature after combining these two. Now they are doing the RDIA. What RDIA is doing? So RDIA is actually doing the finding the inconsistency between the frames, like the temporal and the spatial connections. So here we will see the RDI. The main objective is like to enhance the face feature, to finding the inconsistency between the frames, between so here they are taking the both frames, like the RGB and the depth map as well, and they are finding the residual computation. What is the residual computation? How they are finding the residual? Like they are finding the frame I plus 1 minus frame of I. So by this they are finding the residual, and then after finding the residual computation, they are using the residual attention, which is actually explained here. The residual attention we can see from here. why is this important? Because residual attention is that which is actually focusing on the temporal aspect and the spatial aspect both. First, what they are doing, for the both, let's suppose about the RGB residual, they are passing the RGB residual to the regional attention, and they are using the 3 2D convolution to just again finding the more features. And after finding those features, these features are passed through the spatial attention to finding the, the more the important feature, and attention in the spatial domain, in the RGB features. And similarly, in if toward the frames, between different channels, the temporal attention between the channels. Here the main, all both are the similar, but the main difference is here is, if we can see here, this 3D convolution. So they are applying the 3D convolution after this GLU activation function, because this is along in the spatial, between the RGB features. So they are using 1 cross 3 cross 3 kernel, but this is along the channel, so that's why they are using the 3 multiplied by 1 cross 1 kernel. So all other both are the same. And again, at the end, they're using the sigmoid function to just nullify the negative values. And they are getting here, they're getting the spatial attention, and here they're getting the temporal. And after that, they are again, after that, it will come here again, residual attention, they are getting the attention RGB. And here similarly, if we pass the the depth map, they will get the depth map weight of the attention mechanism. And again, here if we see from this, because after RDIA, what they are doing, they have to pass to the 3D CNN. So here, because they are passing the F enhance, so they are mixing, they are fusing these enhanced feature with these features. And after this, they are passing to the 3D CNN for the classification. So this was their main model. Like the 3D CNN is actually classifying either this is the real or the fake. And because this is the supervised technique, so this CNN is using the ground truth, which actually they have used, they use the ground truth. And here the depth map is coming from the phase depth map transformer. So this was the supervised techniques. And again, the experimental setup, loss function, they use the structure similarity index and the MSE mean square error to evaluate between the estimated and the ground truth phase depth map. And for the evaluation metrics, they're using the detection accuracy, but the main important is the AUC, because the AUC give us the, the detection accuracy on all different thresholds. 8 video frames, and each frame is resized to 224 cross 224, which is exactly the getting the face, face part of the from the videos. For the training, they use the Adam optimizer with these parameters. Hardware is the RTX 3090. The main the main important thing about they have done the intra database and the cross database. What does it mean? Like the intra database, they train their model on face forensic data set, and they test it on the same data set. So that this is the intra database. So so they train on the same data set, and then they test it from the same database. And they got 1.66% improvement to the baseline model. They have some using the baseline models. And the database, the cross database, for the training they have used the face forensic, but for the testing they use the calib df dataset. And on the cross database, they are getting the with different, they're using the baseline as an exception. They are getting the improvement plus 10.08% improvement, percentage points improvement. So they are showing the generalization as well. So but again, they use the different because the backbone, what does the backbone is doing, because they're extracting the feature from the backbones, the RGB feature. So they tried 3 different backbones, the exception, the ResNet 50, the FENet. But the overall in their model, they are using the exception. And they are doing some ablation studies with these backbones. And they came to know like the exception is getting the higher AUC improvement on video level. So that's why in their proposed model they're using the exception. In the conclusion, the depth information advantage, because in previous studies, they claim that no one was considering these auxiliary information, especially the face depth maps. So that's why they include, and they propose their own model, the transformer model, to get the more realistic and the high detection accuracy based on that. And they propose these three models with some already proposed state of the art models, and they are considering they have done the strong cross data set generalization training on one data set and testing on the other data sets. Here it's come the weakness and some potential future directions. About the weakness, the first, if we see here RDI, their modules, this is MD, this is RDI. If we see here, first they're finding the residual computation, then they are doing some attention. Again here, then residual attention is again, spatial attention, temporal attention. So again, even MDA, they both are the highly computational expensive. So they are the highly computationally expensive, and again, the results and improvements are mentioned, but the flops, the frame per seconds, and the inference time, they didn't mention. Maybe their model is performing good, but in flops and frame per second, there would be the huge difference, which should be considered. And the residual attention module, they use the initial 3D, 2D convolution blocks, and they never tested in ablation studies, like if they remove these three module, what will happen, or maybe include more more convolution layers. They never tested in ablation studies. What about the future direction? Future direction, it's very interesting problem, and it really shows very interest, because we can use the other auxiliary information. Like nowadays people are using the multi models, so we can use the like the other auxiliary information, such as the frequency domain signal, with this phase depth maps. So maybe it can increase the detection accuracy as well. So it will came into the multi-model domain. And again, because their transformer model is supervised based technique, but here we can replace this with the self-supervised or semi-supervised method to reduce the dependence of manually generated ground truth depth maps. And the acknowledgement, they are doing the acknowledgement to these database they are using, and their UST as well. So this was the whole about the paper. Thank you very much.